Electrochemistry is the study of generation of electricity from the energy released during spontaneous chemical reactions, and the use of electrical energy to carry out chemical reactions that do not proceed spontaneously. The study of electrochemistry helps us in creating new eco-friendly technologies because the reactions carried out electrochemically are energy efficient and less polluting. A large number of metals, such as sodium and magnesium, compounds like sodium hydroxide, gases like chlorine and fluorine, and many other chemical substances are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. In human beings, the communication between the cells and the transmission of signals through the cells to the brain and vice versa have electrochemical origins. An electrochemical cell is a device that is capable of either producing an electric current due to chemical action or of producing chemical action due to the passage of electricity. There are two basic types of electrochemical cells. They are voltaic or galvanic cells and electrolytic cells. In voltaic cells, the chemical energy of a spontaneous redox reaction is converted into electrical energy. Voltaic cells are also called galvanic cells. The electrical energy produced by such batteries can be put to useful work, powering our cell phones, radios, and other devices. In electrolytic cells, electrical energy is required to carry out a non-spontaneous chemical reaction. When you recharge your cell phone battery, you are actually running an electrolytic cell. We will be focusing on voltaic cells in this module. Before we discuss how voltaic cells work, let's review the basics. Oxidation occurs when one or more electrons are lost. As a result, the oxidation number of a species increases. Shown here is an oxidation half reaction. Silver metal can lose one electron to form a silver ion. Reduction is defined as the gain of electrons. Note that the oxidation number of a species decreases when reduction occurs. For example, when a zinc ion gains 2 electrons, zinc metal is produced. We talk about half reactions because they only describe half of what is happening. If one species loses electrons, then another species must gain electrons. Oxidation cannot occur without reduction, and reduction cannot occur without oxidation. In an electrochemical cell, both oxidation and reduction must occur. Having trouble remembering the definitions for oxidation and reduction? Just think of an oil rig. Oxidation is loss, reduction is gain. Which of these represent oxidation? Which represent reduction? Equation 1 is an oxidation half reaction. An electron is lost and the iron 2 ion becomes iron 3. Equation 2 is reduction. The aluminium ion gains 3 electrons to form aluminium metal, and the oxidation state of aluminium goes from +3 to 0. Equation 3 is a reduction equation. Electrons are gained. Equation 4 is oxidation. 2 electrons are lost. When building a voltaic cell, one often starts with a half cell. A half cell, or a redox couple, consists of a metal electrode immersed in an aqueous solution containing the metal ions. A copper half cell is illustrated here. 2 half cells must be connected to build a voltaic cell. The electrodes are connected by an external wire through a voltmeter and a switch. This, however, is not sufficient for the voltaic cell to run. A salt bridge connects the solutions. The salt bridge allows migration of ions between the half cells while preventing direct contact between the half cells. In this diagram, the salt bridge is a U-shaped tube containing an aqueous salt solution, such as potassium nitrate. In some voltaic cells, a porous frit is used, or both electrodes may be immersed in the same electrolyte solution. When the switch is closed, the circuit is complete, and electrons move through the external wire. The migration of electrons through the external wire creates a current that can be used to run a motor or some other electrical device. The electrode where oxidation occurs is called the anode, and the electrode where reduction occurs is called the cathode. To help you remember this, think of an ox and a red cat. Oxidation occurs at the anode. Reduction occurs at the cathode. Let's consider what is happening at the electrode-electrolyte interface. Metal ions from the solution have a tendency to deposit on the electrode, trying to leave the electrode positively charged. Simultaneously, metal atoms from the electrode have a tendency to go into the solution as cations, leaving the electrode negatively charged. These two processes are competing. Depending on which process has the stronger tendency, a charge separation results. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentrations of all the species involved in a half cell is unity, the electrode potential is known as standard electrode potential. As per IUPAC convention, standard reduction potentials are now considered as standard electrode potentials. As mentioned earlier, the anode is the electrode where oxidation occurs. The anode has a negative potential relative to the solution. By convention, the anode is considered the negative electrode in a voltaic cell. The cathode is the electrode where reduction occurs. The cathode has a positive potential relative to the solution. By convention, the cathode is considered the positive electrode in a voltaic cell. The voltaic cell we've been discussing is called the Daniell cell. The net ionic equation for the Daniell cell is given here. Zinc metal reacts with copper-2 ions to form zinc ions and copper metal. Since oxidation is a loss of electrons, the oxidation half reaction has zinc metal losing 2 electrons to form zinc ions. Reduction is a gain of electrons. So, the reduction half reaction has copper-2 ions gaining 2 electrons to form copper metal. We know that oxidation occurs at the anode. So, zinc must be the anode. Copper must be the cathode because reduction occurs at the cathode. Electrons travel through the external wire from the anode to the cathode. By convention, when drawing voltaic cells, the anode compartment is shown on the left and the cathode on the right. Generally, voltaic cells are represented using a shorthand notation instead of a diagram showing the half cells. In this notation, a galvanic cell is represented by putting a single vertical line between the metal and electrolyte solution, and putting a double vertical line between the two electrolytes connected by a salt bridge. Using this notation, a Daniell cell may be represented as shown here. Under this convention, the EMF of the cell is positive and is given by the potential of the half cell on the right-hand side minus the potential of the half cell on the left-hand side. That is, the EMF of the cell is equal to E right minus E left. Using this convention, the EMF of a Daniell cell may be calculated as shown. In an operating voltaic cell, electrons flow from the anode to the cathode. The current flows from the positive electrode, the cathode, to the negative electrode, the anode. This current flow takes place when the circuit is closed, because a potential difference exists between the two electrodes. The potential difference between the two electrodes is called the cell potential or the cell electromotive force, or EMF for short. Cell voltage is measured in volts. The potential of an individual half cell cannot be measured directly. We can only measure the difference in potential for two half cells. To simplify this, reduction potentials are measured relative to an arbitrary standard, called the standard hydrogen electrode. You will learn more about the measurement of electrode potential in the next module. You have learned in the previous module that the potential of an individual half cell cannot be measured. You can only measure the difference between two half cell potentials, which gives the EMF of the cell. If the potential of a half cell is arbitrarily chosen as the standard, then the potential of the other half cell with respect to the arbitrary standard can be determined. Arbitrarily, the standard hydrogen electrode is chosen as the standard reference electrode. The standard hydrogen electrode consists of a platinum electrode coated with powdered platinum inside a glass tube. The platinum electrode is dipped into a 1 molar solution of hydrogen ions, and pure hydrogen gas is bubbled in at 1 bar of pressure. The standard hydrogen electrode is designed to carry out the half reaction shown here. A hydrogen ion plus 1 electron produces half a mole of hydrogen gas. By convention, the potential of the standard hydrogen electrode is assumed as 0 volts. When all ion concentrations are 1 molar, reduction potentials are called standard reduction potentials or standard electrode potentials. The standard electrode potential of an unknown half cell is determined experimentally by combining it with the standard hydrogen electrode. The EMF of the resulting galvanic cell is determined using a voltmeter. As the potential of the standard hydrogen electrode is assumed as 0 volts, the measured EMF itself becomes the standard electrode potential of the given half cell. For example, the standard electrode potential of a zinc electrode is determined by combining it with the standard hydrogen electrode and then measuring the EMF. The EMF of the cell is calculated as the potential of the right electrode minus the potential of the left electrode. Therefore, the EMF of the cell is equal to 0.76 volts. Thus, the standard electrode potential of zinc is equal to minus 0.76 volts. The negative value of the standard electrode potential indicates that zinc can reduce the H+ ions. Similarly, the standard electrode potential of copper is calculated as shown here. The positive value of standard electrode potential indicates that cupric ions get reduced more easily than H+ ions. In other words, hydrogen ions cannot oxidize copper. Thus, copper does not dissolve in HCl. On the other hand, copper dissolves in nitric acid due to the oxidation of copper by nitrate ions. The values of standard electrode potentials of some electrodes are shown in the table here. If the value of E0 is greater than 0, then the reduced form of the species is more stable than hydrogen gas. If the value of E0 is less than 0, then hydrogen gas is more stable than the reduced form of the species. As can be seen from the table, fluorine, with the highest standard electrode potential value of plus 2.87 volts, shows the highest tendency to get reduced to fluoride ions. Hence, we can say that fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium ion, on the other hand, with the lowest electrode potential value of minus 3.05 volts, shows the least tendency to get reduced to lithium metal. Thus, lithium ion is the weakest oxidizing agent and lithium metal is the most powerful reducing agent in an aqueous solution. You can also see from the table that as the value of the standard potential increases, from the bottom to the top of the table, reactions show a greater tendency to undergo reduction. The strongest oxidizing agent are found at the top, while the strongest reducing agents are found at the bottom of the table. As the value of standard potential decreases, half reactions have a greater tendency to oxidize. The reactions in the table need to be flipped to write out the oxidation half reaction, and the sign for the electrode potential changes. That is, the standard oxidation potential is equal to minus standard reduction potential. Try to answer this question on your own before checking the answer. Which of these is the strongest oxidizing agent? The nitrate ion, elemental iodine, or the dichromate ion? Answer: the dichromate ion is the best oxidizing agent. As shown in the table, it has the most positive reduction potential. Sometimes, inert electrodes, such as platinum, gold, or graphite rods, are used in voltaic cells. Inert electrodes provide a surface for electron transfer to occur, but they don't participate in the reaction. If inert electrodes are used, then the electrodes do not change in size as the spontaneous reaction proceeds. The potential difference between the two electrodes gives the cell potential. For voltaic cells, the cell potential is always positive. To calculate the EMF of the cell, add the potential for the cathode half reaction and the potential for the anode half reaction. The electrode with the positive reduction potential acts as the cathode, while the electrode with a negative reduction potential acts as the anode with respect to the standard hydrogen electrode. We'll develop our skills by completing a practice problem. Consider this situation. A student constructs a voltaic cell by connecting a half cell containing silver wire immersed in 1 silver nitrate and a half cell made from aluminium wire immersed in 1 aluminium nitrate. Identify the anode and the cathode in the cell. Write the balanced net ionic equation that occurs. Calculate the EMF of the cell. Identify the direction of electron flow in the circuit. Identify the direction of ion movement through the salt bridge. Which electrode will get larger? Which electrode will get smaller? There's a lot to do here, so we'll work through the problem one piece at a time. Let's start by consulting our table of standard reduction potentials. The silver half reaction has a higher standard reduction potential than the aluminium half reaction. This means that silver has a greater tendency to undergo reduction than aluminium. Since silver has the higher standard potential, silver will undergo reduction. Aluminium has a greater tendency to oxidize, so we will need to write an oxidation half reaction for aluminium. Since reduction occurs at the cathode, silver will be the cathode in this voltaic cell. Aluminium must be the anode, since oxidation occurs at the anode. Now that we've identified the anode and the cathode, writing the half reactions is easy. At the cathode, a silver ion gains 1 electron to form silver metal. The value for the standard reduction is plus 0.80 volts. At the anode, aluminium metal loses 3 electrons to form an aluminium ion. Compared to the standard reduction potential table, we have flipped the reaction. Notice also that the sign of the electrode potential changes as well when we write the oxidation half reaction. We need to balance these half reactions to show the conservation of change as well as mass. To do this, we must make sure that the number of electrons lost equal the number of electrons gained. In this problem, we need to multiply the cathode half reaction by 3. However, reduction potentials are intensive properties. Note that the value of E0 for the reduction half reaction is unaffected. Now, we are ready to find the overall balanced equation and calculate the cell potential. Adding up the two half reactions gives the net equation. 3 moles silver ions react with a mole of aluminium metal to form a mole of aluminium ions and 3 moles of silver metal. To calculate the cell potential, just add the cathode and anode potentials. We get E cell is equal to plus 2.46 volt. We have enough information now to draw a diagram of our voltaic cell. Electrons will flow through the external wire from the aluminium strip, the anode, to the cathode, silver. When the switch is closed, anions will flow from the salt bridge into the anode compartment, and cations will flow into the cathode compartment. As the cell runs, the aluminium electrode will get smaller, and the aluminium ion concentration will increase in the anode compartment. The silver electrode will get larger, while the silver ion concentration in the cathode compartment will decrease. Consider a voltaic cell, such as the Daniell cell we studied earlier. If an external opposite potential that is less than the cell potential is applied, the reaction will continue in the forward direction. If instead an external opposite potential is applied that is equal to the cell potential, the reaction stops altogether. There will be no current flow. If the external opposite potential is larger than the cell potential, the cell will now run as an electrolytic cell. The reverse reaction will occur. Electrochemical cells have a variety of uses. For example, pH meters use electrochemical cells. Electrochemical cells can also be used to measure solubility product constants and other types of equilibrium constants. They are also useful in potentiometric titrations.